We will start now with what we call as the, we call this particular method the class, there's something wrong with my pen. It's like this. The operator method. Now, in the operator method, all the derivatives in your differential equation are replaced by capital letter D. So if some of you have already read a soft copy of the differential equations by Rainville or the differential equations by Bidient, the operator method actually writes all derivatives of your unknown function as capital letter D. Now, how do we use this particular method in determining the solution of non-homogeneous differential equations? So, for you to be able to understand it, I'd like to go straight to a particular example. I'll stop sharing for now, class, and share again because of that thing that appears in my board. Okay. Now I have this sample problem number 1. I'll go straight to the discussion during the course of the giving you the steps for the solution. So you have d squared minus 1. Now we enclose it by y being equal to, this is y being equal to e raised to x. Now, if this is written not in the operator manner, this is actually to be written as y double prime minus y being equal to e raised to minus x. So what we did here is just we replaced the second derivative by the operator d. I've discussed it already, the operator d, which is raised to 2. So this actually operator d is equivalent to the derivative of your unknown function with respect to your independent variables. Oftentimes, our independent variable is x and our unknown function is y. So in this case, you get to see here the y, meaning you are having the second derivative of y minus y equal to e raised to minus x. What I like about this particular operator method is it could be treated just like a characteristic equation wherein we can write down the corresponding factors of this particular original DE when it is written in this form. What do I mean? So you can write the d squared minus 1 in this factored form like d minus 1, d plus 1, and then you have y equal to e raised to minus x. Now, you see that this minus d minus 1 and this d plus 1 is actually d squared minus 1. So these two equations, actually these three equations just mean the same thing. They all represent the same thing. Now, our goal in operator method is we will isolate the y on the left side of our equation, meaning we will transfer these two, the d minus 1 and the d plus 1, on the right side. So we will do that. That could be done by the process of division. So you will have a 1 over d minus 1. Then you have a 1 over d plus 1. And you will have here, so I have transferred these two in here, and you will have it multiplied to e raised to minus x. Okay? Now you have transferred these two. Now the next that you will do is, of course, you need to integrate this. By the way, you need not integrate the left side because it's already y. So you only need to integrate the right side in this case. So you need to write the integral here, and whatever is your answer here, that would be your particular solution already. As for the complementary solution or the complementary equation, you can go back to the characteristic equation wherein this d minus 1 and d plus 1 is replaced by m minus 1 and m plus 1. That is, if you like, that what you're going to have here is simply the particular solution. But if you want everything to be in here, like all the C's, the C1 and the C2 that appears in your complementary equation, you can also do that. But I don't want this particular equation to be so crowded with so many terms that I only want to determine now the YP. Now, then the next question probably that will come into your mind is how will you treat these two? You have the 1 over d minus 1 and the 1 over d plus 1. Now in DE, there is this particular formula that we use, and I'd like to write it on the next sheet, that will use the negative 1 here and the plus 1 here in processing the entire expression that you have on the right side. And what is that? So I will write on the next sheet what is that, and I will explain based on what is written. So your y now is equal to the integral of, I will first write what you have here. So it's e raised to x, wait class. So you have here e raised to x, integral of e raised to minus x, times you have e raised to, by the way, this is minus x, e raised to minus x, times the integral, so this is class times, the integral of e raised to x. Then I will have here e raised to minus x dx dx. So I will explain why I have this. If you notice class, here you have a minus 1, a d minus 1. How will you use a minus 1 here in the d when you write your integral later on? The minus 1 there is this minus 1 that you are seeing here. This is the minus 1. And it is automatic. Look, huh? So this is d minus 1. So the minus 1 that you see here is this minus 1 here. If this is minus 2 or minus 3, this becomes also minus 2 or minus 3. What about what is written before the integral? What is written before the integral is the same function that you have here, meaning it's an exponential function, but its exponent is the negative of what is written here in your integral. So you have here e raised to minus x because of the minus 1, then the exponential function that should be written before the integral should be plus 1. Now, this particular first set of e raised to x, integral of e raised to minus x, addresses the presence of this 1 over d minus 1. Okay, 1 over d minus 1. Now, I'd like to change color for you to understand what we're doing. Okay. Now, what about then this one? The d plus 1. So we'll go here on our next slide. You notice this? It's plus 1. So the exponential, the argument of your second exponential function on your second integral is also positive. Since this is positive, the exponential function that should be written before it should be negative. So you see this one? It's positive x. This one is negative x. This one addresses the presence of this. So if you have several, you have, let's say, for example, a 1 over d minus 1 times a 1 over d plus 1 times 1 over a d minus 2, you will have to add here another integral depending on the factors of the d, of the operator that you see here. Now, by the way, it's a requirement in the operator method that this left side is factorable. If this is not factorable, for factorable rather class, you don't need to use the operator method because it will only work for such cases. But in terms of what is written on the right side, the g of x, that is, it does not have any limitation if compared to the method of undetermined coefficients. The method of undetermined coefficient requires only that your g of x will fall on as either as an exponential function, a constant, a polynomial, or a combination of this, even a sine and a cosine. This one, the operator method, can have an ln, can have a tangent, It doesn't have any limitation on the g of x. Its limitation is in here on the left side. It requires that your operator d, your polynomial in the operator d should be factorable. So, okay, so I hope I have explained that well. So in here, this is now your first, this is your 1 over d minus 1 times, since it's being multiplied here, you are also going to multiply here. So times this integral, which is e raised to x, because this is already d plus 1. And of course, outside, it will have e raised to minus 1. So whatever is the sign of the argument here after the integral, the opposite of that should be written before the integral. Now, what about this one? Where is this? This one came from your original given g of x. So we'll have this as another color. So this g of x, the e raised to minus x is written here. So it's the last thing that you are writing, your g of x. Now, y2 dx dx, you will learn in integral calculus that whenever you have multiple integrals, the number of the integral symbol is corresponding to the number of the differentials here. You cannot have this process if you only have one dx here. You have only one differential of x. And this is it, class. All you have to do is integrate. So let's integrate in this case using the operator method. So if you will integrate, if you notice, this e raised to x and e raised to minus x is e raised to 0x. And that would simply be 1. So I will copy, I have e raised to x, and this 2 which is being multiplied, I will copy as e raised to minus 2x. Okay? Then I have an integral which will now be e raised to 0x, which is 1. So then this would be a dx dx. Now you will process this integral first. So you have e raised to x, and by the way, I will have this as yp. So e raised to x, integral of e raised to minus 2x. And this one, the integral of that is, of course, x. And you have here dx. Since this is particular solution, I will not anymore write an arbitrary constant here because I want this to be the particular solution. So I will not anymore write the c here. But if you want your y resulting from this integration to be the complete solution already, then you need not write yp here. But you need to write here the constant of integration. So the next process that you are seeing here is you need to integrate the integral of x e raised to minus 2x dx. Okay, you need to process this. And of course, that will need integration by parts. So if you use integration by parts, your u is x, your du is dx, your dv is e raised to, let's see, what do we have there? E raised to minus 2x. And your v is equal to negative 1/2 e raised to minus 2x. So if we will use integration by parts on our second term, the second term that this is actually the second and the last integral that we will follow, the result would be this. So you have this as your multiplier. So the answer now will be yp is equal to e raised to x, and then the corresponding answer for this one, negative 1/2 x e, sorry class, this is equal to, samok sa akong pen, equal to, so you have this one, uv e raised to minus 2x v du. So this one, negative, negative, that would be positive. So plus 1/2 integral of e raised to minus 2x. But if you have a direct formula for this that was taught to you by Miss Niti, you can use that one. So your yp is equal to, now you need to multiply this, you distribute it to the two terms. So what will be left of this one is negative 1/2 x e raised to minus x. And this one, if integrated, is actually negative 1/2. So this becomes negative 1/4. So negative 1/4 e raised to, now this is minus 2x multiplied to x, so that would be minus x. So this is your particular solution. Your particular solution for the given differential equation. This original differential equation. As for its complementary solution, it is dependent on the roots that you have here. So since your roots are 1 and minus 1, your roots are 1 and minus 1, so your yc should be c sub 1 e raised to x plus c sub 2 e raised to minus x. This one is based on what you've learned in the method of undetermined coefficient in terms of the nature of the roots. So I have simply mentally replaced the operator d here by m, and that would give me roots which are real and unique from each other. Then that would then corresponds to exponential function having those as the argument. Then the complete solution of your DE will just be the sum of these two. So the complete solution of the DE will be the sum of the YC and the YP illustrated in the previous sheet. And that's it, class. You just add this two, that is already the solution of your given differential equation. So let's say, for example, we'll copy it. So you'll have c sub 1 e raised to minus x or e raised to x. Then you have c sub 2 e raised to minus x. Now, for your particular solution, you have this negative 1/2, negative 1/2 x e raised to minus x. Now, look closely, class, that your second term is e raised to minus x, negative 1/4. In terms of form, it's comparable to this. Only this one is having a constant that is not specified. Whereas in here, it's specified. So you can still have them combined. So you can still have them combined as one. So now you will have them represented only by this, C2e raised to minus x. Because C2 minus 1/4 is still another arbitrary constant, which could still be represented as C2. So your complete solution for your differential equation, your original differential equation would be this using the operator method. This is your original DE, by the way. And if you recall our discussion in method of undetermined coefficient, if you use the method of undetermined coefficient here, you will be forced to modify the form of the particular solution. Because in terms of form, this is a e raised to minus x, which is similar to c sub 2 e raised to minus x. So if you recall, if they're similar, like this one, this is similar in form to this. So you need to modify. That is why you get to have this x e raised to minus x. It's actually a safer procedure to do compared to the method of undetermined coefficient, because you can readily, you can easily forget that you need to modify your particular solution with the method of undetermined coefficients. In this case, or in the case of this particular method, even if you forget, the answer will take care of that, because this one is already your modified particular solution if it's done using the method of undetermined coefficient. So this is your method, or what we call the operator method. I'd like to give another example on this. That way, you will appreciate the operator method over the lengthy procedure of the method of undetermined coefficient. So I will use something that will have a combination of procedures. Let me just check, class. Look for a sample that will be a combination of such. We have the integral Okay. This one. This will be very long if you will use the method of undetermined coefficient. So I'll write the DE here. So this is D squared times D plus 4 squared y equal to 96 e raised to negative 4x. If you will use the method of undetermined coefficients, you will have until the fourth derivative. Because if you'll have this expanded, this will be d squared plus 8d plus 16. And you need to multiply everything, all the terms here by d squared. In terms of factoring, you won't have any problem though. But in terms of processing your particular solution, you will have a problem. Why? Because in the first place, class, you need to modify your particular solution here because of this. You have a root which is negative 4, similar to this one. So your particular solution will be modified not only once, but twice because you have two roots equal to negative 4. That's the problem with the method of undetermined coefficient. But if you are the type that will not easily forget the pitfalls, and that is there's a need for you to modify your particular solution. And if you're the type of student who doesn't matter whether you're doing it long method, then the method of undetermined coefficient is the right method for you. But if you are the one who would rather have things done in a shorter manner of time, this is how you do it. So you will process this piece by piece class. What do I mean? You have only d plus 4, sorry d plus 4 here, squared y. And what I'll do, I'll transfer the 1 over d. I have 2 1 over d's because this is d squared. And this is to be multiplied to 96e raised to negative 4x. We call this class the inverse operator. So take note of that. It's the inverse operator. And seeing this later, when you process your non-homogeneous differential equation, means that you will integrate your given g of x, this is your g of x, depending on the number of 1 over d factors you see. Since you see two 1 over d factors, that would mean that this will require that you integrate 96 e raised to minus 4x twice. So now you're learning something new. When you see the inverse operator, that means you are to integrate your given g of x depending on the number of inverse operators that you see, or depending on the number of 1 over these that you see on the right side of your DE. Keep the left side for now as d plus 4 raised to 2y. We will keep it that way. So I will process this. So if we will have it integrated, this will be divided by 4. So this will be integral of negative 24 e raised to minus 4x dx. Because I need to get 4 from 96, that way I will complete my EU du here. So if I get 4 from 96, what is left is negative 24. But still, I need to perform another integration. So I will get another negative 4 here. So then the answer would be 6 e raised to negative 4x. Right? So that would be your 6 e raised to negative 4x after you have integrated 96 e raised to negative 4x twice. Now, but still you see that your left side has still the d plus 4 squared. So how do you go about it? Just like my first example, it's time now to isolate the left side. So you will have to write y equal to 1 over d plus 4. And then you will have here 1 over d plus 4. And you will have it integrated with 6e raised to negative 4x. Now, you see that you have 2 of this. And by the way, don't write the integral first because you haven't yet converted this 2. So just like my previous example, since this is, this is plus, so you will have here e raised to minus 4x integral of e raised to 4x. That takes care of that. The other one multiplied to another e raised to minus 4x integral of e raised to 4x, primarily because that's positive. So this 2 takes care of this, just like in the first example. Then we will copy the 6e raised to minus 4x. Now you see two integrals, then there should be two differential of x here. So I will just write the second one in here. So now if you will multiply this 2, that would be your 6. That would be your 6e raised to 0, or that would simply be your what? That would simply be your 1. So you will have now e raised to minus 4x integral of e raised to, that would be e raised to 0, and then that would mean 1. So there's no need for you to write this, right? And you have the integral. Look at this. The integral of that's e raised to 0, and this is e raised to 0, giving you simply 6 dx dx. So see, you'll only integrate 6 twice. And of course, you know that's very elementary for a CHE and an ECE student. Integrating 6 once will give you 6x. Then you'll have dx. Integrating it again for the second time will give you what? That would give you 3x squared. So see, this is your particular solution already. Yp is equal to 3x squared e raised to minus 4x. Your yc will be determined based on the method of undetermined coefficient, meaning you base it on the roots of your auxiliary equation, meaning this one. You base it on the roots that you have in here. Okay? So your roots will be 0, 2 zeros, and 2 negative 4. So I will write here. So that's your YP for now. So if you have 2 zeros, then you have a YC and 2 negative 4. So you will have C1x e raised to minus 4x. You modify the first term. Then C2